Hello students, we will now begin the third video that will continue to lead us through the first packet dealing with electrochemistry. This will be our lesson on cell potential. If we think about the numerous outlets throughout our home and throughout the classroom, they standardly are ready to deliver 120 volts of electricity whenever we need it. So, for example, we may have a toaster at home that is continually plugged into the wall. Well, then are electrons continually coursing throughout the toaster? Well, actually, not until the lever is depressed is there a potential created or a downward slope for the electrons to flow. So actually, they're just there, ready to be used. It is not again until a potential is created. So from that standpoint, now we want to move into how cell potentials apply to our galvanic or voltaic cells. Cell potential, which is also called electromotive force or EMF, has this wonderfully beautiful symbol, and we are usually reserving it to conclusively describe the entire cell, the oxidation and the reduction, although we can have an EMF value for the oxidation reduction and for the reduction reaction. Usually, we have that wonderful knot, which is referencing standard state. Which recall, that means 25 Celsius, 1 atm, and now we are finally seeing where really the 1 molar requirement for the concentration of solution will come into play. The cell potential is the driving force. It is the pull for electrons, or in essence, the steepness of hill that's created for electrons to flow. Cell potential is symbolized in volts. A volt is defined as 1 joule per coulomb. A joule is a unit of energy, or coulomb is a unit of charge. We most commonly measure the cell potential that is going through a circuit with the use of a voltmeter, which we will utilize those specific instruments when we do some electrochemistry later in the year. So if we can look at some standard reduction potentials, you're always provided reduction reactions, and the EMF values for those reduction. And if we look from top to bottom, we have our most positive values, and then as we go downward, they get lesser into the negative realm, more negative. All right. These have a strong pull for electrons. The fluorine, lead 4 oxide, the gold +3 ions. These have a very, very strong pull. So the more positive your value, if it's a reduction reaction, the stronger the pull for electrons. Whereas we go down, these do not have a strong pull for electrons. In fact, these would rather be oxidized. If we look at some of these species, lithium +1, we know wants to undergo oxidation of the lithium neutral. The lithium ion does not have a strong pull for the electron because this is its stable state, it's octet. Same with potassium +1 and calcium +2. Where if we look at the type of species that have big positive EMF values for the reduction reactions, fluorine becoming fluoride, cobalt-3 becoming just cobalt-2, gold +3 becoming neutral, chlorine diatomic becoming chloride. So knowing the chemistry of our elements, that should make total sense to us. Now, if I could call your attention to this half cell that I've identified here, we have 2 hydrogen ions taking on 2 electrons to become diatomic neutral hydrogen in the gaseous state. Notice it is an EMF value of 0 volts. That is known as the standard hydrogen potential. That actually has been assigned, and all these other values have been calculated based upon it. Just like fluorine being assigned a value of 4 for electronegativity, carbon-12 as the standard for atomic mass units, and so on. So let's look at a common example that would require us to pull information from this table, and it will show, and I hope bring meaning to what these actual values imply. And I know I'm probably repeating myself, but again, there's no need to memorize these values. You will have access to this as you're doing your unit assignment, of course. You'll be provided this on the next exam, and of course on the AP Chem exam. All right, so what if you were asked this? Order the following oxidizing agents in order of increasing strength under standard state conditions. So if these are being oxidizing agents, they themselves are undergoing reduction. So the strongest of these would have the strongest or the greatest positive value in volts for the half-cell reduction reaction. All right, so we want to find where we have chlorine as a reactant. So as we're looking. Oh, there's chlorine gaseous, adding 2 electrons to become the chloride, and that is a positive 1.36 volt. Well, then we want to look for hydrogen peroxide. Oh, there we go. And forming water, positive 1.77 volt. Then we want the iron plus 3. Now, there's iron plus 3. Ooh, but that's just plus 1 electron forming iron plus 2. Now, we do want to check to see if there's any other iron plus 3 reaction given, because maybe this has to happen in multiple steps to make neutral iron. So, I don't see iron. I see iron plus 2. I don't see iron plus 3 anywhere else. So that must be our only reaction to use as a comparison, and that is positive 0.77 volt. So in order of increasing strength, this would be the weakest, and then we'd have hydrogen peroxide, and then the chlorine. Let's look at another example. What if we were asked to order the following reducing agents in order of increasing strength? So if they are reducing agents, they themselves are undergoing oxidation. All right, well, what do we do with that? Because we are just given reduction reactions. Well, what we have to find is the opposite. We have to look for hydrogen being a product or the reverse of what these reactions are. Okay, well, what do I mean? Okay, we want to find hydrogen, again, as a product, and it will have lost electrons and have formed a hydrogen ion. Well, let's see. Okay, where do we have hydrogen, diatomic? Oh, this reaction here. Oh, so this is assigned a value of 0. So hydrogen, 0 volts. Aluminum. Well, let's see. Where do we have aluminum? Sometimes, honestly, we know that aluminum forms a plus 3. Sometimes it's easier. Right there. So aluminum, plus 3, that's the reduction. But in the opposite direction, aluminum would be giving up 3 electrons to form the aluminum plus 3. But this negative 1.66 volt is describing the reduction. We need to describe the oxidation. So we need to flip this, which we know will flip the sign. So this gets a positive 1.66 volts. So far, aluminum, 1.66 volts. Well, let's look at copper. Now, most stably, copper forms plus 2. Well, here I have, but that's the copper ion. There's neutral copper, and it would form the copper plus 2. Now, that's a positive 0.34 volts for reduction, so then we want the negative 0.34 volts to describe the oxidation. So if we are ordering these in increasing strength, Aluminum would be the strongest with, the oxidation voltage of 1.66, then hydrogen being 0, then our copper. All right, so let us see an application of where we can use this specifically with half cell design. All right, so if you were given this kind of a question, you were given the cell reaction. Well, let's see, the anode, which will be the oxidation, is going to be here, zinc. The zinc solid creating the zinc ion. And then our reduction, copper to copper neutral. Now let's make sure that we balance. One zinc, fantastic. So we have to balance charge, 0 plus 2, so we need to add 2 electrons here. One copper, we have 2 electrons, so we need to add 2 electrons here. Oh, and if we look, we have to gain the same amount of electrons as we lose. Perfect. So that gives us our overall reaction that we have here. Now, we need the EMF for the cell. All right, let's get our reduction first. So we go to the table, and copper plus 2 electrons has an E naught value of positive 0.34 volts. This is our oxidation. So we have to look at the reduction that will be the opposite of this, and we have to reverse its sign. And so this E value is positive 0.76 volts. Just like we add the half reactions to get the overall reaction, we add the half cell potentials to get the overall EMF of the cell. And that will be here 1.10 volts. For the galvanic or voltaic cell to be successful, it needs to have an EMF that is a positive volt value, and the greater the better. Here at the bottom of this are some things to note. Because we're only given reduction reactions, we're going to have to reverse one of our reactions. I'll show you in a moment which one we know to reverse if we're given both reductions. It's the one that's going to then deliver a positive EMF of the cell overall. If we would have had to do any multiplication through our half reactions to make sure that the number of electrons given and taken was the same, we do not change our EMF values. The only thing that you can alter about the EMF values is the sign if you reverse the reaction. EMF, cell potential, is an intensive property. Intensive. It doesn't depend on the amount. So if you had to multiply this through by 10, this EMF stays the same. Divide this out by 5. This EMF stays the same. The only thing that can happen is that you reverse the sign to get the overall positive value for your cell. I'm going to pause and go ahead and get another video ready that will take you through the next step if you're not given the overall reaction, but you're given the reduction reactions, how we would treat those kind of problems.